an oscilloscope that y'all are fixing to get into are the functions of the oscilloscope that y'all need to know how to use for this class. This is actually what we call a digital oscilloscope. So analog is definitely more precise, but the problem we have with analog is trying to deal with infinity. So if we go to digital, digital deals with steps or what we call ones and zeros. So it's very easy to represent ones and zeros with voltage levels, right? You understand that, which is pretty neat. So the analogy we use, if I'm trying to send you information and I was trying to send it to you with a flashlight that had a variable resistor on it, right? You understand? And I was changing the intensity, and every intensity meant something different, it would be impossible for you to figure out what I'm trying to change. But how easy would it be for me to send you the light is on or the light is off? So the big advantage of digital is being able to send it over long distances, right? Very easy to store. The electronic circuits that handle ones and zeros is a lot less complex than the circuits that handle analog information. So now we live in a digital world. You know, even though it sounds like analog to us, it's not, because of what we hear and what we don't hear, what we see and what we don't see, which is pretty interesting. So a digital oscilloscope is actually a computer. So we can do a lot of neat stuff that's hard to do with analog. I don't know if you can see this little word right here. Can you see what that says? Storage. Yeah, so it's ones and zeros. So it's memory. So we can store signals in memory. We could download them and put them on a USB stick right here. We could take them to another scope. We could hook them up. We could pair signals. So you know, John's out there troubleshooting. He don't know the symbols, right? So he could download it and bring it back to the shop and show the boss what he saw and do that kind of stuff. Also, it can do math for us, you know, which is hard to do with an analog oscilloscope, but we can do math with it. We can store it. We can do a lot of neat stuff. We can change languages. We can have this thing display the frequency for us, which we call frequency counter. So it can count frequency for us. It can make measurements for us. It can do a lot of neat things that's hard to do with a regular analog oscilloscope. But all we need to understand is we need to understand how to measure voltage. For this class, we need to know how to measure voltage and time. So what an oscilloscope actually measures, whether it's an analog scope or a digital scope, the main thing it's measured is a voltage level relative to time. Okay, y'all understand that? It displays time on the horizontal axis, which is this guy right here. It displays volts on the vertical axis, which is this guy right here. So this is vertical. This is time. So we measure volts this way. We measure time this way. Everybody understand? So if I come up here and put this on DC, of course, it's just going to, so we can measure DC with an oscilloscope. So I'm going to come up here and hook this up. And I don't know what voltage this is putting out. Okay. So you notice all I get is a straight line. And what we have is we have a line right here that's called, so this is what we have. We have two channels. Now what dual channels mean, so here's, you got two probes we can hook up. They're called in a channel 1 and channel 2. Some oscilloscopes call it channel A and channel B. It's not that much difference. So we could actually look at two different things at the same time. Well, what we do is we set what the scope sees as 0. Right here it's got a yellow number 1. And notice I can change the reference of what is equal to 0. Now, normally when we're measuring DC, we don't want to put it in the center, right? You understand why? Because that reduces the accuracy or the resolution of the scope. So normally we move it down toward the bottom. I usually use the line above in case it does have some type of negative component to it. I can actually see it pretty easily. So what we do is right here, this is called, this control, y'all can't see it, I got it covered up. It's called volt per division. And it's up over channel 1, volt per division. I have channel 1 turned on, so it's lit. So right now channel 2 is not even turned on. So see, I can turn it off or turn it on. Okay. And so I look over here, it says I'm looking at 5 volts per division. When we're talking about divisions, we're talking about these major divisions right here. Can y'all see the lines? So this would be 5 volts, because I have my 0 set right here. This would be 5 volts. That would be 10 volts. This would be 11, 12, 13 volts. Now what we have is we have 5 minor divisions in between each major division. So that means if it's in 5s, then each minor division is going to be worth a 1. So that's what do we say? A volt. You notice if I vary the voltage, it makes sense. So that's basically kind of like a meter. But instead of it displaying what I'm measuring, it actually shows you a representation of the actual voltage. So if you measure minus DC, you'd probably put your 0 reference right here. So this right here is called position. And notice with this one, I'm changing what we talk about when I change the position. I'm changing the position of where 0 is at. Y'all understand? Not too hard. Of course, if I come up here and put it on 2 volts per division, oops, then what's the matter? Yeah, it's off the screen because I've got 2 volts per division. So I've only got 2, 4, 6, 8, 10, 12, 14 volts. All that means is I'm looking at more than 14 volts. So what we need to do is we need to put more volts per division, right? Does that make sense? So to make the display smaller, we put more volts per division. But I don't want to put it on 10. I don't want to put it on 10 volts per division. So now the scope is less accurate, right? That makes sense. So what we're trying to do is we're trying to get the biggest display we can possibly get and not have it go off the screen. Y'all understand that? And how do we change the volts? Using the what? Volts per division. So right now I don't have anything hooked up to channel 2. By the way, as soon as you turn a channel on, it brings up a menu of things that's relative to that channel. And we'll look at this later on. In fact, to turn it off, if you hit it once, it'll bring up a menu. I'm sorry. You turned it off then. So if you don't see it lit up, it means it's what? Off. So there's the menu for channel 2. And up here at the top, you can't see it, it's kind of too bright. Channel 2. Right now we have our coupling at ground, we have our volts per division at course, and we're using a ×1 probe. If you think about it, the highest volts per division I have on an oscilloscope is I have 10 volts per division. So that means right now the maximum I can measure would be 10, 20, 30, 40, 50, 60, 70 volts. Right, you understand? What if I needed to measure more than that? Well, what we do is we get what we call an attenuated probe. Most of the probes, standard probes now, are what we call. This says time. I don't know if you'll see it right. It says ×1 × 10. So what happens is when I put this probe on ×10, we call it a ×10 probe, but actually it divides by 10. And why do they call it a ×10 probe if it divides by 10? Yeah, that's what you're saying. You do it the same way, count the divisions, but it's telling you to multiply your answer by what? 10. So it's called a times 10 probe. So if I had times 10 and I had my zero set right here, that'd be 100, right? If this is 10 volts, that'd be 100, 200, 300, 400, 500, 600, 700 volts that I could measure with this scope by using a times 10 probe. Actually, we could measure more than that if I dropped it down to the very bottom. But I usually don't do that on DC because sometimes we have signals that do go negative, right? Especially in digital. We have what we call overshoots and undershoots and that kind of stuff, and we want to see that type of garbage that's going on. Out of US Steel, we had a times 100 scope probe. We used it to measure SCR packages that was running off of a 440 AC. And so we used the times 100 probes. So to increase the range of the scope, what you do is you just use a multiplier probe. Now what's nice about a digital scope is I tell it what probe I've got. So if I come up here and say a times 10 probe, then what it does is it does the math for you. So you don't have to do the times 10 in your head. Does that make sense? You just read it like you normally would. But your volts per division change. So see now it says 100 volts per division instead of what? 10. So what's nice about a digital probe is that a digital scope is you set the probe multiplier that you're using, and then it automatically adjusts the ranges for you. It got the name times 10 from the analog probes. From the analog scopes. We don't have the ability to do that. So it was called a times 10 probe because you had to make your measurement and multiply it by 10. On this scope, if you left it on times 1, you would have to do that. But if you put it on times 10, it automatically adjusts the ranges for you and attenuate the input by that, which is pretty neat. And you see it covers a times 10. I've never seen a times 5 and a times 50. The only thing we had at US Steel was times 10 and times 5. Now most of your probes now, a times 10 is so popular that it comes with a switch on the side of it where you can change it from what? From times 1 to times 10. Yeah, it's called reference on this probe. This is the first probe I've ever seen. The problem we have is what is zero? What is zero? So what we have the ability to do here is we can switch the tip over to ground, so we'll actually see where zero is actually at. Does that make sense? Yeah, on digital scopes we don't have that problem because it has a thing over here that shows us where zero's at.
So you can still keep the other first ground, or part of that part
Yeah. Well, no, it connects to ground. It connects to ground through the scope.
So no, both parts are ground.
Well, the tip is not grounded; it's switched over to ground.
Okay.
So you're not going to blow stuff up if you switch it to reference. So what it does is it takes the tip and switches it to ground. Not the tip, the circuit that feeds the tip.
Yeah.
That makes sense? It's just like over here, we got another place we can do that, is that you can see the ground reference right here by putting it on ground. Now you're not grounding the tip of the probe, you're grounding the input of the amplifier. So we actually see exactly where zero truly is, right? You understand? Normally on a digital scope that's not as important because it shows you where 0 volts is at. You can see it right here. For channel 1, I've got a little 2 over here. What's nice about a digital scope too is it displays the channels in different colors. Analog scopes, everything's the same color. So you lose traces, you lose that. Yeah. And this has been true for a long time. You get multiple probes in a circuit, you lose track of which scope probe is hooked up to channel 1 and which is hooked up to channel 2. We used to take a piece of tape and just wrap it around one of our probes, wrap it around both ends, and then all you had to do is see which one had the tape on it, which channel it was on. What they do now is put these little clips right here, And what you can do is a little semicircle made out of plastic, and then you can clip it on to the scope probe. And then you're supposed to clip it on right here. I don't have it on that one, but it's on this one. And what that does, it makes it real fast for you to figure out which probe is hooked where. And it's kind of like when you have multiple meters. That happens to me all the time. You got black and red leads. And I'll be trying to measure voltage, and I measure 0, and I realize I've got the black lead off of 1 meter and the red lead off another. I've done that more than once. So we did that a long time ago, and here we're not using actual scope probes. This is not actually a true scope probe. This is just this guy right here works out great. This scope probe costs around $50, and people break them. They don't understand how to take care of them. This cable that we let y'all use is worth, we pay about $3 for this. If we mess up one of these, we don't cry. But the problem is that these give you problem at extreme high frequencies. So if I was going to get into like high-speed digital or anything that was really had a high frequency, I would not use one of these. But what are we dealing with here? We're dealing with 60 cycles. So these guys work great. Like I said, they only cost about $3 a piece. We buy these in bags. So if you mess up one of these, it's no big deal. You understand? But I'm not going to let you use one of them. Now, if you go out and buy your own scope probe, you can buy them at Forbes Electronics up on 4th Avenue. Then, if you want to bring it in, then it's fine. But, are we okay? So, I think I explained this to you too. So, this little lead right here, this is the ground lead. Now, that's the biggest difference between an oscilloscope and a meter. A meter does not have a ground. It's got a black lead and a red lead. That black lead is the common for your meter. It's not the common for your circuit. So you can put that black lead and red lead of a meter in anywhere in the circuit you want to. We can't do that with an oscilloscope. An oscilloscope, this right here is connected to earth ground through the power plug. And we do, out at US Steel, they have what they call isolation transformers that you can buy for an oscilloscope. And you can plug it into the wall and plug your scope into that. And what it does is it disconnects the ground from the oscilloscope. Now, the big problem you have there is that now you can put that black lead anywhere in the circuit, but all these little old metal things take the polarity of whatever you use the ground to. So we had one at US Steel. They put it inside a Marcato box because we had to probe inside SCR packages. And you change your scope, you use rubber gloves. Because as soon as we put that black lead across an SCR, the chassis was over 600 volts. The metal chassis of the scope. So here, this is not as bad because it's all double insulated. But this is ground right here. And be real careful. It's real convenient when you pull this off. But to eliminate a lot of the electromagnetic interference that these guys would pick up, they bring the ground all the way out to the tip of the iron. So this right here is ground. If I took an ohm meter and went between here and here, or if I went to the ground plug on my power plug and measured out here, this is going to measure 0 ohms. So I've seen people blow these guys up by taking that cap off and probing inside a circuit and let that sucker right there touch up against something. So you got to be real. I've seen these. That's a big magnet there. I've seen these little old leads right here just vaporize. Where people take it and they hook it inside a circuit, a high power circuit, and it just vaporizes it right in their hand. You know, that's not. So remember. Now we're going through a isolated transformer, but as soon as you pop one of these things down, you've established common for the circuit, right? Or you've actually established a ground on the circuit, and you cannot probe through the circuit with this guy right here. You can with this guy right here. Now we do have the ability to tell our scope to subtract this probe from this probe, which is what that's what voltage drop is. Y'all understand that? So what is a voltage drop? Well, if you measure relative to common, and this is what we was talking about the other night when we got over there. When we make circuit measurements, usually we make them relative to common, right? And we don't probe a lot in the real world. We do in electronics, but out there in power and stuff like that, power supplies, we don't probe two probes around in a circuit. Now what we do is establish what is common and what is ground, and we'll put one of our meter leads there, and we'll get an alligator clip and we clip it there. And then we go around and we probe with one probe because it's a lot what? Safer, yeah. So you learn real quick how to probe when we make measurements relative to one another. You know, so I could have a DC circuit. Or an AC circuit, it doesn't make any difference. And then I use my meter, so let's say we have 2 resistors, or even 3, it don't make any difference. And then I take the black lead of my meter and put it there, and then I come over here and put it there, and of course, let's say over here we measure 120 volts, and then I move my red lead right there, and it measures 80 volts. What would be the voltage drop of the resistor? Huh? 40 volts. And that's all your meter does. If I take the meter and put it right here, it's going to measure 40 volts. But if I measure relative to a common, then each one of these devices are going to drop a certain amount of voltage. So how did you come up with that common? Yeah, you took 120 minus what? 80. Well, we've been able to do this with oscilloscopes for years, is to tell it to subtract one of the channels. On the analog scope, what we do is we invert one of the channels and we tell them to add. Now, on the digital scope, we just come up here and go to our math function. So right here where it says math, then it throws another section on here. And then by now we got it set up to do what? You'll see the sign? Subtract channel 1 from channel 2. Now in DC it would make a difference. You'd have to figure out channel 2 would be your common and channel 1 would be the high side. On AC it makes no difference. So we'd tell it to subtract channel 1 from channel 2, and then I would probe through with these red leads. So I could put the red leads anywhere I want to. So I could put it across a resistor. And my scope would subtract channel 1 from channel 2, and it would show me the results. This scope actually brings up a green chart that shows you the math operation. An analog scope, you can't do that. So if I want to probe inside a circuit with two of my leads, then what I do is I just tell my scope to do what? Subtract the 2 channels. That makes sense? Which is pretty neat. Okay, so let's pop AC on this thing. Let's turn off channel 1. So I'm going to come over here and take this device called a function generator. And what does a function generator do for us? Generate signals. AC or AC superimposed on DC. So we can superimpose it. Oh, no, that's the right stroke. Yeah. So I'm going to come up here and I got my coupling on DC. Oh. Okay. One thing that gives people a lot of problems is AC and DC on the oscilloscope. Right now we're not going to use AC on the oscilloscope. I don't use the term DC. I don't use the term direct couple for oscilloscope. I mean direct current. I call this direct coupled. Direct couple will measure anything. It shows you what is there. So if I want to measure AC on the oscilloscope, I use the DC coupling. If I want to measure DC on the oscilloscope, I use the DC coupling. It is not direct current, it's direct coupled. If I want to block DC, I put it on AC. So the only time you should ever use the AC on an oscilloscope is if you want to block DC. And right now we don't want to block DC. And we'll see later on. We're going to do it later on when we try to look at the ripple voltage on it. So I'm going to put it on direct couple. Why I can't see anything is I'm telling it I've got a times 100 probe, and I have 500 volts per division. So 500 volts per division to a 3 volt sine wave looks like ground, right? You understand? So what I'm going to do is, okay. Add it on DC coupling, and we'll talk about the course too in a minute. So I got it on DC coupling, I got it on course. We got math turned on. I don't know. You can see the tape somebody's put around here to identify. You see they have a piece of tape over here, which is okay. The problem with masking tape is over time it gets easier to go away. It says it's grounded. It's got a little ground. So this is AC. Yeah, something is still going on. Here's math right here. Math is green. We're going to see it green. For some reason, the multiplier wasn't right. So what we're trying to do, this is my volts per division. What are we trying to do? Okay, so if I go to 2 volts per division, you can't see the watt. Okay, you can't see the tops and the bottoms, right? You understand. So what does that need to do? I need to go up 1. So that's 5 volts per division. But I don't want to be 10. So what you're trying to do is make it as big as you possibly can without doing watt. So now notice I'm measuring AC. So where do I put my common? I put my ground, my 0 volt reference down the center line again, right? I have it on 5 volts per division. Now the problem with trying to measure AC, think it a little bigger, is that if you got minor divisions on the top and the minor divisions on the bottom, it makes it hard to see. So what I do is I come up here and shift my 0 volt reference until I get this the bottom one on a line. Does that make sense? So now I'm not trying to do minor divisions on the top and minor divisions on the bottom. And then what I like to do is I like to shift this till I can shift this. So here's your horizontal position right here. So notice it, can you see it moving back and forth? Okay. What I like to do here is I like to get the tip on where I can see a minor division. So if it's out here on the center somewhere, it's real hard to see a minor division. So what did I do? I shifted over. So y'all understand what we did? So what did I do? I shifted this up to a horizontal line so I can count from a 0 now. Then I shifted this over to one of these vertical lines that has the what? The minor divisions on it. So I got it on 5 votes per division. That'd be 5, 10, 15, 20, 21, 22, 23 votes. Peak to peak. So what would that measure on a meter? First of all, what would I do? I divide this by 2 and get what? Then P, and then multiply it by 0.707.
8.1.
And so that'd be 8.1 votes R minutes, right? Are we okay? You okay? 23. Another way you could do it, especially when you get in, so let's drop it down. So it's too small, so I want to make it bigger, so I'm going to put less votes per division. So that's 2 votes, that's 1 vote, that's 500 millivotes. 500 millivotes is too small, right? Because I can't see the wall, top and the bottom, right? You understand? I didn't want to do that. Okay, this is 1 vote per division. I can take this and line it up till it's on a line. Now the problem is, if it's 1 vote per division, how much is each minor division worth? 0.2. Y'all understand? Because we got 5 minor divisions. How do you come up with 1? If you got 5, if you divide 1 by 5, you come up and get what? 0.2. Okay? Everybody understand that? So this would be 1, 2, 3, 4.24 votes. And of course, this is as small as we can turn this guy here down. We can't get this all the way to 0. Now another way you can do it is you can count the number of divisions, but if you count the number of divisions, your minor divisions are going to be worth 0.2, right? And then multiply it by this. A lot of people will do that. I learned a long time ago how to count. That way I don't have to have a calculator. Okay, so what's the frequency? This is labeled time per division. So notice when I do this, it spreads out because I'm putting less time per division. So I'm making my scope go faster. And then I come up here, and now we have this. Now, if I'm going to measure time, what do we want to do with this? We want to spread it out as far as we possibly can. Okay, stretch it out as far as we can and still see a cycle. Is this a cycle? No, because I can see this, but I can't see it fall back down. So we got to drop back 1. Okay, now I can see a cycle. Or actually see more than one cycle. Then I can take this and I can move it until now I'm looking for a vertical line, right? You understand? Now I have a place I can count 0 from. I have it on 250 microseconds per division. This is unique on a digital scope. On your analog scope, your vertical and your horizontal run in exactly the same units. So you notice on here that the vertical went 1, 2, it goes 1, 2, 5, 1, 10, then it goes what? Right? Understand what we're saying? It goes 1, 2, 5, 1, 2, 5, multiples of 1, 2, 5. And on an analog scope, your horizontal goes in multiples of 1, 2, 5. So it'd be like 1 millisecond, 2 milliseconds, 5 milliseconds. Then you go to what? 10, 15, right? You'll understand that. I'm sorry, 10, 50. Okay. This has 250 microseconds, which makes it a little harder to figure out what each one of them is worth, right? That makes sense? So let's do it this way. Let's count the number of divisions. We're going to count in ones. So if I'm counting in ones, and each one of these minor divisions is worth what? 0.2. So I'd go 1, 2, 3, 4, 5. By the way, notice I don't have it zeroed anymore. It don't make any difference on an alternation when you measure time. No matter where I have this at, if I come over here and put that right there, so I'm going from the rising side of this guy to the rising side of that guy, it's going to be the same time no matter where you measure it on the alternation. Does that make sense? So I'm going to go 1, 2, 3, 4, 5, 6.2. So I'd say 6.2 times 250 microseconds, and that would give me the time. So what's the time? 1.55 milliseconds. And then we would take the reciprocal of that to get the what? Frequency. Everybody understand that? That's on your formula sheet. That's basic. Because frequency and time are inversely proportional. So that means if they're inversely proportional, if we know one, we can get the other one by taking the reciprocal of it. Now this is what we have on a digital scope that we don't have on an analog scope. You can actually see the A to D conversion. You can actually see the wave moving in steps. You don't have that on a digital scope, on an analog scope. So on an analog scope, this waveform would be just as smooth as it possibly could do. But a digital scope has to go from an analog to a digital back to an analog, right? You understand, which is pretty interesting. And it does this by displaying things in steps. We call it volts per step if you're into A to D conversion or analog to digital conversion. So we don't deal with infinity, so what we do is each step represents a certain binary number. So can y'all actually see the steps? Yeah. The little steps right there? I'll probably show out if I increase the frequency. I can't get to that. So that's just something on a digital oscilloscope that you just get used to, is actually being able to see the steps, and you understand that they're not what? They're not really there. This is a nice smooth signal, so it's not moving in these steps. If you take digital and you get into analog to digital conversion, if we have time, this will make a little sense. PLCs, advanced PLCs, if you're in that, we'll talk a little about A to D conversion and how we take an analog signal and represent it as a binary number, which is pretty neat. So we have a certain resolution to the thing, depending on how many bits are in the A to D conversion. Another thing we have to do, of course, is we have to synchronize the scope with the signal itself. And we refer to that as trigger. So here's your trigger. This brings up the trigger menu. So the option is, y'all won't have to do anything. The only thing you'll probably have to change is what you're synchronizing the scope to. This is the source. I'm synchronizing it to channel 1. Y'all understand? Because that's what I'm using. What we do to synchronize the scope is we tell our scope to look at a certain voltage level. So right now it's out of sync. And this shows you that what I like about these scopes is they show you where the trigger's at. Excuse me. So this says T. And notice when I move my trigger down into the signal, sorry, that's the position here. As soon as I move it down inside the signal, sorry, I shouldn't have done that. I cheated. Yes. I switched it over to channel 2 while ago. By the way, if you get lost on this scope right here, you got this little button right here. It calls what? Auto. And it will display. It won't be correct, but it will display something. It'll change the setting on the scope for you to get it in a range that you want to. This is the cheat button right there. But let's switch it over to channel 2. So if you ever see it and you look at it and it appears to be jumping all around and moving around like that, what does it mean? It means it's out of sync, right? I understand that. And you got to come up here and try to figure out. If I move the trigger, I don't know if you can see, but the T over here turned blue, which is the color for what? Channel 2, right? You understand that? So we're trying to trigger on channel 2. So I'm going to hit trigger menu. I'm going to come back here and change this over to channel 1. You can do that. You can do external, so you can actually trigger the scope on something that you're not looking at. We're not going to use that feature here, so we're either going to trigger on what? Channel 1 or channel 2. Everything that we're going to look at are going to be synchronized signals. So that means if I'm looking at the AC input and I'm looking at the DC output, we can sync. Normally we sync. If I look at the output of the transformer on channel 1 and the output of the rectifier on channel 2, then we can synchronize on either one of them, right? You understand? But if I'm looking at two different signals that have nothing to do with each other, then sync on the scope won't make any difference. So that's about all we need to know about the oscilloscope, is how to trigger it. So I got it on the external trigger. Another thing that I like about a digital scope, an analog scope, what we have on an analog scope is we have 10 horizontal positions on an analog scope, but we have 8 vertical lines on the analog scope, which is the same here. So if I count these, we have 10 this way and we have 8 that way. All right. What they do on a digital scope is we have 12. If you keep the menu up, you can see 10, just like you do on a standard analog scope. If you turn the menu off with this button right here, then you get 12. You don't get any more vertical divisions, but you get 2 more horizontal divisions, which means it makes the setting on the scope, you can be a little more accurate with this guy than you can with an analog scope. But all these are exactly the same on an analog scope. So on an analog scope, we have volts per division. We have the position. We can turn the channels what? We can turn them on. We can turn them off. We have a dual. These are called dual channel oscilloscope. So we have 2 channels, channel 1, channel 2. We can turn on, turn them off. What I like about this one is they're different different colors. On the analog scope, you're constantly trying to figure out which one's which. We don't have that problem with the digital scope. Trigger. So to set your trigger, you get the trigger menu. That brought your trigger menu up here. Then we're going to set ours to edge trigger. There's a lot of triggers we're not going to look at. We're going to do channel, whatever channel you want. The slope determines where the trigger's at. And this is where it's this on an analog scope, what you trigger on is always on the left hand side. On a digital scope, this is what you're triggering on. So I'm saying trigger on the what? On the positive going slope. Well, you see the first slope I see past this arrow is what? Is a positive slope. If I come over here and change it to a negative going slope, notice the first slope we see on this arrow is the what? The negative going slope. When I bring the trigger up, the white line is exactly where we're triggering at. Can y'all see that? This really becomes important, like in digital and stuff like that, because in digital we time with rising edges and falling edges. And if we're timing with a rising edge, then I want to reference my scope to a rising edge. If we're timing on a falling edge, we can reference our scope on the falling edge. AC, it don't make any difference which slope you use. Just as long as you understand what the slope is. And that's about all that we need to talk about here. We got all type of patterns we can trigger on, but that's some high level stuff. But we want edge triggered, channel 1 or channel 2, whatever slope you want to use is fine on power supplies, right? And then leave this on auto mode. This really makes a lot of difference. So that's about it. On button is where? On the top. The probes are over here on the shelves in a box labeled scope probe and function generator probes. So we use the same probes for the function generators we do here. We're not going to be using a function generator much in this class. Most of our stuff is going to, that's not true. When we get into transistors, we're going to use DC to power the transistors up, and then we're going to make them amplify stuff. And we're not going to let them amplify Alabama Power. We're going to let them amplify signal, right? You understand? So we're primarily going to use this guy to generate the signals that we're going to. This is not considered a power source. It's considered to be a signal source. And they're really neat for troubleshooting, especially stereo equipment and stuff like that. Because if you've ever seen audio is all over the place. So it would be impossible for me to look at the frequency response of an amplifier while it's actually operating. What we can do with a function generator is I can inject a signal into it, and then I know what I'm putting in, and I know what to expect out, right? You understand? Because I'm putting the signal in. So if you're going to troubleshoot stereo equipment or stuff like that, well, no, the actual stereo. This guy here has modulation on it, which is what we do when we put information into when we send information through media, especially we have a term called multiplexing. Anybody know what multiplexing is? Multiplexing is when we let multiple information share the same medium. And what's media? Media is what information flows through, right? You understand? So right now, this is air. So this is the media I'm using right now. I'm using air. That's my media, right? Because my sound waves are traveling through the air. Now, of course, we have no problem with me because right now I'm the only one talking. But if you was to go down to Bryant-Denny Stadium on a Saturday where you go out to the 50-yard line right before kickoff and you're trying to listen to your buddy up halfway, you can't hear anything because they're multiplexing, right? You understand? Because now we have multiple information sharing the same medium. So what we need to do is have the ability to demultiplex through filtering and stuff like that. What we do is we place the information on something called a carrier. And it's usually a frequency that's a lot higher than the information it's trying to carry. And then we transmit that over and we can have multiple frequencies on the same wire at the same time, which is pretty interesting. But then we have to come up and we have to get that off, right? So what we do is we have the ability to modulate this guy here. We have multiple modulations. The two primary, we have what we call AM and FM. Y'all probably heard of that before. On networking, we use something called quadrature phase shift modulation, which is a combination of analog. It's a combination of amplitude and frequency modulation, which is pretty neat, to get a bunch of information on it. Well, so what we do with this ability, this guy, we have the ability to modulate. So placing information on a carrier is called modulating. Stripping the carrier off is called demodulation. So we have these devices we hook up to our cable called a modem. What is a modem? It's a modulator demodulator. So when I put information on the cable, it places it on the carrier. When information comes into the modem, it strips the carrier off and lets the information come through. So we can modulate and demodulate with this guy. The frequency counters, the function generators that y'all be able to use. And this came in real and handy because I got an old radio I'm working on that's having problems with the AM channels. So I can actually take this and modulate it and wrap it around the antenna. And I can set the carrier frequency, and then I can dial the radio into that carrier frequency and hear the tone. It's a tone on that one. So it makes it really, really neat. So if you're working on stereo equipment, if you're working on radio equipment, then you get one of these things, you need to be able to have that modulation, demodulate, or build your own modulator. So that's by the way, this is actually two pieces of equipment. It's got a function generator on it. I mean, it's got a frequency counter on it. And then it's got a function generator. The three waveforms we can generate on most function generators is we can generate a sine wave, or variations of a sine wave. We can generate a pulse waveform, and we can generate what we call a triangle wave. And that's your three primary AC waves. There's a what? Sine wave, pulse waveform, and a triangle. And this gives us the ability to do all that, just by every function wave. This one up here, this is where you set your range of frequencies. So right now I've got it on 2 kilohertz, so I can go from almost 0 up to 2 kilohertz. Well, actually a little above. And what you need to do is you need to set that as low as you possibly can, because the higher you set it, these adjustments get more. I mean, you get that sucker on the 20 megahertz, you barely turn that dial, it's going to be jumping a lot of frequencies, right? This is where you get your output right here. It's labeled output. And this is a frequency counter. Can you see this right here? It takes, frequency counters are slow because it's going through an analog to digital conversion. So we get people trying to set frequencies, and they'll come up here and turn these things, and they don't understand it takes a little while for your frequency counter to do what? Catch up. So that people do what they call oscillation, overshoot, undershoot, overshoot, over. It's kind of like some people you see when they run off the side of the road, they get scared and do what? They jerk it and then they're over in the other lane, then they do what? Then they jerk it back. I saw a guy do that same thing today. He was all over the place because he got scared instead of coming back on it real slow. So if you're going to use this, you need to be what? You need to turn it a little bit and just sit back and take your time and let it update. But you notice the oscilloscope the oscilloscope changes instantly. So you can see it change time instantly. But frequency generator is okay. I wish we didn't buy them with these things. I mean, the frequency counter, I wish we didn't buy them with these. Normally when we teach AC, we tape them over, because what we want people to do is learn how to measure the frequency on the oscilloscope, right? Instead of on the watt, instead of on that thing. But y'all more than welcome to do that. Fine adjust, coarse adjust, so you can get this thing pretty close to any frequency you want. We won't use this for power supplies. We're going to use Alabama Power. I will show y'all some advantages of high frequencies and when we get into actually power supplies, the advantage of a switching power supply over a linear power supply. Because a linear power supply, your filters have to run the load for the time between peaks, right? You understand? If I can make those peaks closer together by increasing the frequency, that means the size of your filters can go way down. And that's one of the advantages of the switching power supply. So what we're doing, guys, so hopefully we're going to go ahead and go to lab. We're working on our unregulated power supplies. So right now we're just trying to get the transformer on the trainer, right? We're using the transformer on the trainer. We're doing half wave. And then we're putting the filter capacitor across there. Be careful with the what? Polarity. The video I showed y'all the other night. By the way, I did put that up on Blackboard. So capacitors are rated in two things. What's the two things they're rated? Farads and voltage. Farads is their storage capacity. So the bigger the capacitor, the better the filter it is. But the problem is the bigger the capacitor, it's just like car batteries. The bigger the capacity of the car batteries, the more they're going to cost you, right? And that's exactly the same thing true. You go out and buy a battery for your riding lawnmower, and then go out and buy a battery for your, not a car battery, for a big round diesel truck, right? You compare the cost. Yeah, there's no telling how much a diesel battery, that diesel takes a lot of power to crank, especially in winter. I can tell you a story about that. We went up to Joplin, Missouri to a school, and while we was up there, it was in the wintertime, and we drove a diesel car, and it had a plug on it, had a little heater in there that you plugged in overnight, so it would crank the next morning. And there was no plugs outside, so we had this real long extension cord. We ran out of our hotel room, and we plugged it into a wall outlet. But we didn't realize the wall outlet was a switched out. So every time we turned the lights off, what happened? That car had 2 batteries in it. We got up the next day, and what wouldn't happen? Our car would crank. So if you ever run a diesel. Are we okay? All right, guys, let's go. Test reviews up there. It's up on Blackboard. Y'all need to check it, make sure. And yes. And the oscilloscope. There's going to be some questions about the oscilloscope on there. This is our main one of our what advantage does an oscilloscope have over a meter?
Precision.
It should not precision. In fact, meters are more precise. I mean, anytime I come up here and I say, well, anytime you use the term about, that's about 1.2 divisions. You're getting an approximation, but it shows you exactly what's there. So if we got problems with electromagnetic interference, if we got problems with our power supplies, I can measure that, and we'll try to do that. You know, we think power supplies are nice and beautiful, but every one of them has a specification called noise or ripple that they tell you. And if you get outside those ranges, noise on the power supplies is really, really a problem in digital, because in digital everything's turning off and on, right? You understand? So you're putting constant different loads on your power supplies all the time. So what happens is you get this switching noise on your power supply, which can cause you all kinds of problems. You can't see that with a meter. So a meter, you can look at a meter and it shows 5 volts. Then you get your scope out there and you see all that garbage riding on the top, and you say, well, heck, I wonder why, that kind of stuff. So what's nice about a meter scope is the scope shows you exactly what's there. So you can see my function generator has a little problem maintaining frequency. Can you see it? Can you see the time? Yeah, it's shivering. Yeah, so that would not show up on a meter. No way a meter would see that. But now, and that could be causing a problem, especially if this was an FM receiver, right? I understand. So you can see shivering. Yeah. All right, guys. You're going left. You're going to take a break. Well,
I said, you got, you have a little,
I know they call some of these guys.
oh, okay.
So he's in somebody's class. I'm not the only one. So hopefully somebody told me that.